Right.
Hello everyone. Today we have the fourth talk for our Transpacific Colloquium series. I'm happy to present Alex Hamilton, who is a professor at the University of New South Wales and is one of the leaders in transport of two-dimensional materials, nanostructures, devices. Alex has made PhD at the Cavendish Lab at Cambridge in 1993 and was awarded a fellowship to continue work there till 1998, and then he moved to the Sydney and became a professor at UNCW. Alex got a number of prizes, and including Outstanding Researcher Award from ARC and Australian Science Prize. Before we start, let me remind you that questions are very welcome with help of this chat window. And we won't interrupt the speaker, but Alex will make one or two stops in the middle of talk for questions. And as usual, there will be opportunity to ask questions at the end. And also it's very helpful if you note a slide number when you write questions. Okay, so Alex, whenever you're ready, please free to start.
Thank you, Dimitri, and thank you everyone for either getting up very early or staying up late to take part. So this is a very unusual way to give a talk, and I'm still getting used to it. So if there are any questions, please put them through the chat. I'm not sure I can actually see the chat window so easily. I
will do questions. Don't worry about this.
So Dimitri has said he won't allow anyone to ask any questions. He's already being very, so please do ask questions and I'm happy to discuss. So today I'm going to talk about some work that we've been doing at UNSW for many years now, looking at holes in semiconductor nanostructures. And you may ask, why are we so interested in holes? And really there's a very simple reason. As you can see, we're based in Sydney, where it's the weather is always beautiful. And so on the left is shown here, let me see if I can make, actually, I need to. On the left is shown here a band structure of a typical semiconductor. And of course, if you transpose this onto the local environment, the Sydney Harbour Bridge matches perfectly with the valence band of most semiconductors. So we should obviously be studying holes in Australia. This is work that has been done by a number of people over several years. But what I'm going to present today is work that was primarily being done by Elizabeth Marcelina, a PhD student and then a postdoc in our group, who's now at NTU, Karina Hudson, who is now a Sydney Quantum Academy Fellow at UNSW, and Ashwin Srinivasan, who now works at Solana Semiconductor in Sydney. But there are many other people who've contributed to this work, both in assisting with the measurements, those who provided the wonderful crystals that we use for our experiments, and then Fabrizio Nicella, who's now at IBM Zurich, and Peter Stano, who worked on the spin accumulation measurements that I will talk about, Olga Gulko and Jan von Delft, who've done a lot of the theory for the spin gap experiment that I will talk about. And of course, we've got lots of discussions with people at UNSW and elsewhere. So the way I will organize today's talk is to give a little bit of background about electrons, holes, and spin-orbit interaction, and say why the interactions between the spin and the orbital momentum really are telling the whole story and not part of the story. Then I'll talk about some new results where we've developed a new technique for detecting spin accumulation. And then for the second half of the talk, or last third of the talk, will be some recent results that just published in Nature, just accepted for Nature Communications, in a new signature of spin orbit gaps in 1D systems. So our group is an experimental group. What we do is we use semiconductor clean rooms and van der Waals assembly systems to make semiconductor and van der Waals heterostructures. We then make nanostructures on these using electron beam lithography, and we make all sorts of different devices, and then use low temperature dilution fridges and other cryogenic measurement systems to look at their electrical properties. So what is it that's so interesting about electrical properties of nanostructures? Well, obviously we always want to make a better transistor and better electronic devices, so we should understand as best as possible how electricity flows in these things, and in particular how we can use quantum effects to our advantage. Now, we've known about electrons and holes in semiconductors for over a century. But what is not so well realized is that the spin properties of electron holes and holes are very different. For conventional charge-based transistors, this doesn't really matter. But for going forwards, it really does matter. The use of spin can allow new types of transistors, such as topological transistors, which is something that Fleet is very interested in. It can be used for storing quantum information, for example, in spin-orbit quantum bits, which I won't talk about, but we also have some work on. And it can be used to create even new topological states, such as topological superconductivity and Majorana modes. So why holes in nanostructures? There's a few reasons. We can have, if we take a two-dimensional nanostructure, so a thin sheet of holes in an ordinary transistor, and then drill a periodic pattern, an array, into this two-dimensional structure in a honeycomb lattice, we can create effectively artificial graphene with this surface superlattice. And then if we use holes instead of electrons, the very strong spin-orbit interaction gives topological insulating states. In other words, we can end up with dissipationless topological edge states traveling along the edges of something that's made out of a conventional nanostructure, but has been artificially engineered to be a topological insulator. In one-dimensional systems, if you take your your holes and now constrain them to only move in a one-dimensional geometry, such as along a nanowire, it has been proposed that coupling that to an S-wave superconductor can give you P-wave superconductivity, and a very nice system for studying Majorana fermions and other topological states, which can be used, for example, for quantum information. And then if you confine holes in all three dimensions, and so you form a quantum dot, and you locate one single hole in the quantum dot, you can use the spin state of that hole to store information. And so there's a lot of interest at the moment in using holes in silicon and holes in germanium to store and process quantum information, because the very strong spin-orbit interaction means that you can manipulate spins at a very high speed. So very fast 2-qubit logic gates have been demonstrated, and in fact recently 4-qubit logic gates have been demonstrated by the Delft group. So the common theme here is it's the very strong spin-orbit interaction that gives new functionalities that you cannot achieve with electrons. So why is this? And the answer is that holes aren't positively charged electrons. There's something different. We teach undergraduates that holes are just, if we have a band structure, that holes are just heavy electrons. But this is not true. Holes have got a really strong spin-orbit interaction, and you can understand the spin-orbit interaction very simply from atomic physics. If I have an atom here with a negatively charged electron whizzing around it, I've got this electron has got a spin state S, and it's got some orbital angular momentum as it goes round and round L. That electron moving round and round in a circle is generating a current going in the opposite direction. And because the current is going around in a circle, by Lenz's law, we generate a magnetic field B, which is proportional to the orbital angular momentum of the electron, which is going round and round. Now, the orbital magnetic field that it generates can interact with the intrinsic magnetic moment of the electron S. So we end up with an interaction energy of the form L dot S. And this is nothing more than the interaction between the spin and the orbit. So that's what happens for a single individual atom. What happens when we join lots of atoms together to create a crystal? In this case, instead of talking about the orbital angular momentum of an electron, we tend to talk about the linear momentum, P is h bar k, of electrons traveling through the crystal solid. And instead of talking about S shell and P shell and D shell electrons in an atom, we talk about bands of allowed energies, the conduction band, the valence band, the split-off band, and so on. So in semiconductors, we talk about the linear momentum P, not the orbital momentum K. So our spin-orbit interaction is replaced, becomes of this form sigma dot K, where K is simply the linear momentum and sigma is the Pauli spin matrix. The very nice thing now is that we can control the momentum K with an electric field. So applying an electric field changes K, and that will now change the spin sigma through this spin-orbit interaction. The other way we can influence the spin properties is to quantum confine the holes. That will quantize K in one or more axes, and as soon as we quantize K, that will immediately have an effect on what the spin is allowed to do. So all we have to do is take electrons, instead of having them going round and round an atom, we have electrons in a semiconductor, for example in silicon, and we immediately get a spin-orbit interaction that allows us to manipulate the spin with purely electric fields. This is exactly what we want. The problem is that the conduction band in almost all semiconductors comes from S-like states, S-like atomic orbital states. So they've got zero orbital angular momentum, and the spin-orbit interaction, therefore, is zero. So for electrons in most wide-gap semiconductors, they don't have any strong spin-orbit interaction, and so you can't manipulate the spins. But electrons that live in the valence band, these come from p-shell atomic orbitals with L equals 1. And so they have a very large L dot S and a very strong spin-orbit interaction. In fact, the spin-orbit interaction for electrons usually comes indirectly from the valence band because of the gap, because of the small gap. So it's advantageous, therefore, if you want to use spin-orbit interaction to achieve new functionalities, to use holes rather than electrons. And then you might ask, well, which material should I use? And if you're used to working with electrons, you're aware that if I look at the band diagram, energy as a function of K for germanium or silicon or gallium arsenide, the conduction band always looks very different for these different materials. But the valence band is almost always the same or very similar. So actually, it really doesn't matter too much which material you use. Any concepts and ideas that you develop in germanium or silicon or gallium arsenide can be transferred from one material to the other. Which one you choose just depends which particular flavor of spin-orbit physics you're interested in. So silicon, you might choose for industrial compatibility. It's indirect gap. It doesn't have values in the valence band. It has values in the conduction band. It's relatively high disorder, so it's a little bit harder to make devices in silicon. You might use germanium, which has an indirect gap. It's now possible to make very low disorder germanium holes, but this is still not a very mature technology, so it's a little bit harder to make silicon, to make germanium-based hole devices. So what I will be showing today is data from gallium arsenide, where we have a direct gap semiconductor, holes in the valence band, very low disorder, mobilities of 1 million or so centimeters squared per volt second, which means that holes can travel at low temperatures over quite large distances. Of course, two-dimensional materials, other van der Waals materials, can also have very strong spin-orbit interactions, such as transition metal dichroic cochionides, but that's a whole other story. So for the moment, I will concentrate just on gallium arsenide material systems where the spin-orbit interaction is strong but not dominant. So we're used to thinking of spin in terms of Zeeman physics. So if I take an electron in a semiconductor or an electron in free space, if I plot the energy as a function of momentum, energy just goes as hk squared on 2. I apply a magnetic field, and every eigenstate splits by an amount proportional to the magnetic field, g mu b. And this spin splitting is isotropic without a spin-orbit interaction. The spin degeneracy is lifted equally for all states, even at k equals 0. It doesn't depend on the momentum at all. For electrons, if you can get a spin-orbit interaction by making the band gap small, so that you mix the conduction band states with the valence band states, you can end up with linear in k spin-orbit interaction. And what that does is, instead of separating in energy two k states, we separate them in momentum. So the spin degeneracy is lifted between the red spin species and the blue spin species, and it's lifted by an amount that is proportional to alpha k. And so you can sort of think of the spin-orbit interaction as a momentum-dependent magnetic field. At k equals 0, there's no lifting of the spin degeneracy, and then as you increase the momentum of the electron, you get a larger and larger spin-orbit effective magnetic field. For holes, the situation is a little bit more complex, of course. We still have, we have a 4x4, for example, Hamiltonian. We can write this down, we end up with a basically p squared upon 2n term, the kinetic term. Now we have Luttinger spin-orbit term, which doesn't exist for electrons, crystal anisotropies which matter, the Zeeman term we were just talking about, and then the spin-orbit interaction terms which are due to anisotropic potentials in the crystal, and those can either be built into the crystal, the Dresselhaus term, or they can be structural inversion asymmetry, the so-called Rushbar term. For holes, these two terms here, which are the ones that are usually used to control and manipulate spins in nanostructures, don't go linearly in k as they do for electrons, they go as k cubed. So instead of shifting the two bands sideways, we end up with a momentum-dependent splitting between the spin-up holes and the spin-down holes. No, I don't need a rest break. The Rushbar and Dresselhaus interaction, these energies are typically about 0.1 millielectron volts. This Luttinger term is of order 10 millielectron volts. So this is really dominant for holes, and it doesn't exist for electrons. So the theory for hole systems is considerably more complex than for electron systems. And actually, it's a little bit surprising that although we've known holes exist for 100 years, it's only very recently that we're starting to understand how holes behave in quantum confined nanostructures. So let's see what happens when we take the band structure of an ordinary semiconductor and we start to apply quantum confinement. So for example, this is a schematic of the gallium arsenide band structure in 3 dimensions. Here's my conduction band, energy as a function of momentum. Here's the valence band. There's the heavy hole band, the light hole band, and the split off band. And now I confine these into a two-dimensional quantum well. So in gallium arsenide, I would make a gallium arsenide quantum well separated by Al-gas barriers, or if you have a two-dimensional system, such as a TMD, you would automatically have confinement there. What happens is you lift now the degeneracy between the heavy holes and light holes because they have different masses, and so you typically only have the heavy hole band occupied with the spin 3/2. Now, what happens? What are the spins allowed to do? What does the spin-orbit interaction do to the spins? For electrons, when you apply a magnetic field, whatever the electron spin is doing, as soon as you apply the magnetic field, the electron spin aligns with the magnetic field. You change the orientation of the magnetic field, the spin will align again with the magnetic field. So there's no preferred spin orientation, and the coupling, the G factor that couples the electron spin to the magnetic field is constant. It's a property of the material. It has a well-known value for gallium arsenide. It's got a different value for silicon, but it's basically set by the material. For holes, the situation is different. This confinement lifts the degeneracy between the heavy holes and light holes, so we only have the heavy hole band occupied. But now the very strong spin-orbit interaction locks the hole spins so that they can only point in the perpendicular to the quantum well plane. They point in the growth direction Z. So the hole spins become icing-like. They only point up or down. No matter what you do with the magnetic field, they want to point this way. And you can sort of see why that might happen in a very hand-waving picture. If I have my two-dimensional system, which the holes are moving in, then L is R cross P, my orbital angular momentum. R, compared to some origin, must lie within the plane. And whatever velocity the hole is traveling with, it is also within this two-dimensional sheet. So both R and P lie within the sheet. So R cross P must point out of the two-dimensional sheet. And so L points out of the two-dimensional sheet. So L dot S, which is my spin-orbit interaction, will be maximized when the spin is also pointing out of the two-dimensional sheet. So I will get, the hole spins will only want to point up or down and never want to point in plane because of the very strong spin-orbit interaction. And tipping the spins into the plane requires me to mix the heavy hole states with the light hole states, which is why everything, which costs me k squared of energy, and therefore explains why everything goes as k cubed. So now for holes, things are very different. The spin-orbit terms are set both by material constants, as they are for electrons, but also by the mixing between the heavy hole states and the light hole states. And that mixing goes as k squared. So my spin-orbit interaction now is spin orbit dot k squared to allow for mixing, so it goes as k cubed. The in-plane G factor is strongly suppressed because if I apply a magnetic field in this direction, the spins are locked by the spin-orbit interaction this way and don't want to align with that spin. But by changing the separation between the heavy hole states and the light hole states, you can change how easy it is for the spins to be tipped into the plane. And we recently showed that you can change it by a factor of 3 very easily just with gate electric fields. So you've got very strong ability to modulate the coupling, the G factor. So that's the background to spin-orbit interaction. Now I want to tell you 2 results relating to that. But before I do, now might be a good time to pause and ask if there's any questions. Okay. Either my microphone's not working.
Could you remind me how large is G factor? So how the Zeeman effect is compared to the orbital one?
So, Dmitry, sorry, can you?
How large is G factor that scales Zeeman effect and orbital effect of magnetic field?
So let me see if I understand. So you're asking how it, I'm not quite sure what you're asking.
G factor for the Bohr magneton.
Okay, so go back to see if I have it. Normally for electrons, the Zeeman energy is just the spin times the G factor Bohr magneton times the external field, right? And the value of that G factor is given by, for example, Langevins formula. And that is set in solids. The electron G factor is usually set just by the material. So in silicon, for example, there's very weak spin orbit interaction, so the G factor is 2 or 1.9996, I think. Right. In gallium arsenide, there's slight spin orbit interaction for electrons, so the G factor is about -0.4. For holes, the first thing is that the spin is not 1/2 anymore, it's 3/2. But the second thing is that it's now very dependent which direction you apply the magnetic field, as we will see later. So for holes, as soon as you confine them, you quantize K. That quantizes your sigma dot K now becomes strongly affected by that. And so, for example, in this case, if I apply a magnetic field along this Z-axis here, the spins can react very easily. So the spins are naturally, they're icing-like. If I apply a magnetic field in the Z direction, they can move up and down in energy very easily. So in this orientation, I get a G factor of about 7.2 for holes in gallium arsenide. But if I apply a magnetic field that tries to tip the spins this way, that magnetic field has to fight the spin-orbit interaction and the quantum confinement. And that energy scale, we said, was about 10 millielectron volts. So to first order, there's no in-plane G factor at K equals 0. The in-plane G factor only comes by mixing of the heavy holes and light holes. So the in-plane G factor is roughly 0.4. It's an order of magnitude lower than the out-of-plane G factor.
Yeah, I see. Thank you.
And this is also true for TMD materials as well. Right? The strong spin-orbit interaction in any 2D system tends to make the spins want to align perpendicular to the plane. So you end up with very anisotropic G factors. So you end up with a G tensor.
Okay, we have another question. What is the origin of heavy and light holes? Will you briefly explain it?
That is a really good question. Can I briefly explain it? I almost think I would need a theorist to do that. Let me see. It's because you have, yeah, no, I can't simply explain it. It's because you have different projections of you've got J equals L plus S, and so you're going to end up with ±3/2 and ±1/2. And because you've got a spin-orbit coupling, this J now couples to the momentum and changes the momentum dispersion, depending on whether you're taking the value of +3/2 or ±1/2. Dimitri, can you give a clearer explanation?
I'm not sure.
So the two band curvatures here are a direct result of the fact that we've got ±3/2 or ±1/2 projection of the spin. But better than that, I can't sort of say super simply. what is necessary to understand, at least for everything I'm going to present, is that in our case, because we've got different masses for the heavy holes and light holes, when we confine them, the lighter holes move up in energy, or in this case, they move down in energy, and the heavy holes don't move down as quickly, so that only, in our case, only the heavy hole band is occupied. So we're only dealing with spins, hole states with spin either plus 3½ or minus 3½ The light holes are further away in energy. And this splitting is of order 10 millielectron volts. So it's a very large energy scale.
You say intuitive why 3/2 are heavy and 1/2 are light and not vice versa?
So this is, okay, all right, I've been caught being inexact. So here in bulk, you can see that the heavy holes have a much smaller curvature than the light holes, which means the mass goes as 1 upon the curvature. So this spin 3½ projection of the holes has a larger mass than the spin 1/2 projection of the holes. So in 3D, I'm quite safe to talk about heavy holes and light holes. In 2D, I'm not really so safe to talk about that, because what actually happens is the masses become anisotropic because of the confinement as well. So we're safer really just to talk about what the spin projection is and not what their mass is.
Okay, we have another question from Philip Bryden. Is it substantial cubic anisotropy in the Latinger spin-orbit interactions, and doesn't influence the properties of 2D heterostructures in terms of in terms of grown direction?
Yes, cubic anisotropies are important. If you're at low K, because the cubic anisotropies are going as K squared, they're not so important. But what it typically means is that if I was to plot Kx and Ky, normally I would have a Fermi surface like this. But what happens is this, when I confine, the cubic interactions mean that I get a sort of a more square Fermi surface. This is a kind of a small correction. The cubic interactions are important, but they come in kind of after Rushbar and Dresselhaus. They're that sort of magnitude. So they're a factor of 100 smaller than this direct Luttinger term. So we do have to consider them, yes.
Yes, thank you.
So maybe I'll move on and see if I can confuse you with some experimental results rather than confusing me with trying to explain what holes are. So let me now tell you about a new technique for detecting spin accumulation. I'm getting fed up with this animation. So how do we generate spin accumulation? Well, in a non-magnetic material, where it was predicted half a century ago that you could have something called the spin Hall effect. We're all very familiar with the Hall effect, where you pass a current down a conductor, you apply a magnetic field perpendicular to the current direction growth, and that causes a Lorentz force, which causes negatively charged carriers to move in one direction, positively charged carriers to move in the other, and so you end up with a voltage difference between the two sides of the metal. The anomalous Hall effect simply means that you replace the external magnetic field with an internal magnetization, and again, so if you pass a current through a ferromagnet, you will also generate a Hall voltage without having to apply an external field, because your Lorentz force is essentially generated by the magnetization of the material itself. The spin Hall effect allows you to generate a spin current in the absence of an externally applied magnetic field or any magnetization. So there's no breaking of the, essentially the time reversal symmetry. What happens is that particles of, as you pass a current from one side to the other, particles of one spin species, say spin down, go to one side of the device, and particles of the opposite spin species go to the other side of the device. Actually, Xiaolin Wang gave me a very nice analogy for this, which is if you think of it a bit like a spin bowler, if you throw a curve ball or spin a ball, it will curve one way if you're spinning the ball one way, and it will curve the other way when you're spinning the other way. So you can think of the electron spin as generating its own momentum-dependent Lorentz force. And so we end up with an accumulation of down spins on one side of the sample and up spins on the other. But this doesn't generate a voltage because we've still got equal numbers of electrons on both sides. They just have different spin projections. So it took 30 years after the prediction that you could end up with a spin Hall effect to actually detect this. And this was done optically by passing a current through a two-dimensional Hall system, generating a spin Hall effect, and then causing recombination just at the edges. So if we have a two-dimensional Hall system, we pass a current, that current jumps from a two-dimensional Hall system to a two-dimensional electron system, and so the electrons and holes recombine, and depending on which way the current is flowing, you'll either end up with spin up or spin down electrons at the holes at the edge of the sample. And if you look at the circular polarization of the light, and this is this very nice experiment by Wunderlich, you see that depending on whether the current is flowing in the positive direction or the negative direction, you get a change in the circular polarization, meaning that you are actually detecting a spin Hall effect. And there was then this demonstration of a spin Hall effect transistor. So this is very nice, but of course it requires, this only works for direct gap materials where you can couple light out, and it requires a very special structure to be able to do it. There are other methods using ferromagnetic electrodes where you can try and detect a spin imbalance using ferromagnetic electrodes, but ideally what would be rather nice is to have an all-electrical way of measuring this spin Hall effect in a non-magnetic semiconductor. So this is what I want to tell you about now. This is some work that was done by Elizabeth Marcelina, Ashwin Srinivasan, and in particular, the idea actually came from Fabrizio Nicela, who's now at IBM Zurich. And the idea is kind of simple. Instead of using recombination of light or ferromagnetic materials, we're going to use a spin valve. So what we do is we'll pass a current down one side of a sample, and then we'll have some kind of a spin valve. As the current flows, it makes sigma minus, spin minus, and spin plus move to opposite sides of the channel where the current is flowing. And these sigma pluses are able to get through the spin valve, the sigma minus isn't, and then that leads to a potential difference between electrodes 1 and 3. There are two ways we could do this. The linear way, which was demonstrated a few years ago, is you pass a small current from 1 to 2, and you have a spin-dependent barrier. So if we have a tunnel barrier, we apply a strong magnetic field that changes the effective height of the barrier for spin up compared to spin down carriers. And so what you see is that the red carriers are able to get through more easily than the blue carriers. And that then means that we end up with a net potential difference. We've done spin to charge conversion because of the spin-dependent barrier. And now we can measure the voltage between 1 and 3. So that's the concept for the linear spin detection. Just to show you how this works, we've made a nanostructure here, which is a representation of it, which is, as the schematic shows, we have 3 electrodes. We pass current from 1 to 2, and we're going to measure a voltage from 1 to 3. This distance here is about 2 microns. It's a typical high mobility gallium arsenide structure. And we've got a small opening, which is our spin valve, and we can change the ability of holes to travel through that valve as we change the voltage on these 2 gate electrodes. So this is the channel here where we pass the current. There's another channel here, and we're going to measure spin diffusion through this barrier here, which is this quantum point contact. And we can change how open or closed that quantum point contact is with the voltage on them. And we see nice conductance steps. And we're going to operate this sort of in the barrier regime, so on the riser between conductance steps. The 2D Hole system we're using has got a density of about 2 × 10⁻11 centimeters squared. It's got a Fermi wavelength of about 56 nanometers. So it's quite high quality, so the mean free path is 4 microns, so it's considerably longer than the size of this structure. What makes this challenging is that gallium arsenide has a very large spin orbit term, so the spin orbit length is rather short, it's only 35 nanometers. So most of the measurement techniques for doing ferromagnetic contacts and so on don't work in this regime. All the measurements are done at 0.1 Kelvin. We pass the current from 1 to 2, we measure the voltage from 1 to 3, and I'm actually going to call that V3, just to confuse you in the next slides. So the two-terminal resistance, if I measure just between 1 and 2 when I pass the current from 1 to 2, and look at that resistance as I change the magnetic field applied parallel to the 2D plane, is symmetric in magnetic field. And as I change the voltage on this point contact, it doesn't change. Sorry, that's the two-terminal resistance from 1 to 3. But the three-terminal resistance now, where I pass the current from 1 to 2 and measure the voltage from 1 to 3, this is asymmetric in the magnetic field because I'm creating a spin accumulation here. And when I reverse the direction of the magnetic field, I don't reverse the direction of the spin accumulation. And so I expect this to be asymmetric. That's a direct consequence of this spin accumulation and then this spin valve. And one can write down what the magnitude of the spin voltage that accumulates across this spin valve is. It's basically just related to the derivative of the transmission probability through this barrier. And you can calculate pretty simply what the spin current is in the linear regime. And what you need to do to work this out is to look at the difference between when you apply a positive magnetic field and a negative magnetic field. So you take the gradient of this thing here, which is this dB of V3, and that gradient tells you how much spin accumulation is happening. So if we define delta as the difference between, as essentially this gradient in the limit of B tends to 0, that is essentially a measure of the spin accumulation. So we've done this measurement for a series of different potentials on the barrier between the main channel and this voltage probe. And if we plot now for different amounts of current, we would expect that if we apply a bit more current, we'd get a larger spin accumulation. And indeed, when we increase the current from the source to the drain, we see that this delta, which is a measure of the spin accumulation, increases approximately linearly up to when we apply about 10 nanoamps, at which point we're starting to enter the nonlinear regime and we start to get a deviation. So this is very nice. In this linear regime here, we get a spin accumulation, the difference in the chemical potential for the down spins on this side and the up spins on this side, of about 1 microelectron volts. The spin current is about 37 picoamps, and so we can calculate a spin Hall angle, which is a measure of the efficiency of which this current that we're pushing from here to here generates a potential, a spin current going this way. And this spin Hall angle is about 7%, which is consistent with previous measurements. So this is nice, but it's an extremely painful measurement to do. These measurements took us about 30 hours because you have to take measurements over a very wide range of magnetic fields and then look for a small change in the voltage. It's super painful. So there must be a better way of doing it. And that's what we're going to look at next. So our new approach is to, instead of using the spin valve here, which is magnetic field dependent, to work at 0 magnetic field. So now in the lower half of this diagram, we're operating at 0 magnetic field. So the barrier isn't magnetic field dependent, it's just an energy filter. If the incoming energy is above the barrier, the particle can get through. If it's below the barrier, it can't. But now what we do is we pass a really large current from 1 to 2. That causes a difference in the local chemical potential between the sigma minus and the sigma plus. We're well outside the linear response regime. And so if we've got a lot more sigma plus accumulating on the right-hand side of the channel than we do sigma minus, the local chemical potential for the sigma plus is higher than the local chemical potential for the sigma minus. These guys can get over the barrier and into this electrode, whereas these spin downs, because there's far fewer of them on the right-hand side near this valve, they can't get through the tunnel barrier, so they don't get through. So what should happen now is this nonlinear voltage should be symmetric in magnetic field. This is the linear voltage that I was just talking about previously, and you can see if we compare this side to this side, the color axis is that linear voltage, and you can see that this is different than here. Over here is different than over here. And that's the linear term, which depends on magnetic field. The nonlinear term should be symmetric in magnetic field. And indeed, we see that the nonlinear term is symmetric in magnetic field, and it shows peaks and dips depending on whether we are here, where there's a large energy-dependent transmission through this, over this barrier, or here on the flat bits where there isn't. So there, not much happens. We can again so what we would expect now is that this nonlinear term should scale as the driving current squared. And if we plot this nonlinear term as a function of the driving current squared up to a current of about 10 nanoamps, we get a very nice relationship between nonlinear voltage and ISD squared, and then it starts to deviate at higher currents. So this is exactly what we saw with the linear voltage. It's scaling nicely as ISD squared, and it enables us to do a very quick and very simple measurement and immediately obtain exactly the same measurement that we got from the linear data, but much faster. So this is the first time that an all-electric spin to charge conversion has been done at zero magnetic field in a non-magnetic material without the use of any magnetic materials. So this nonlinear technique works, as I said, at zero magnetic field. It's much, much faster. For the data that I showed, this measurement here took 30 hours. This measurement here took 30 minutes. So it's hundreds of times faster just to do the measurements. And in principle, the measurements can be done with nanosecond time resolution at zero magnetic field, so we can access spin dynamics. The measurements can be done in a magnetic field or at zero magnetic field, so we can look at how the magnetic field, the applied magnetic field, actually influences the spin Hall effect. One of the problems with doing the spin Hall effect is ideally you should do it at zero magnetic field because you're trying to generate this spin accumulation without a magnetic field. And this technique works for any material with strong spin orbit interactions. So gallium antimonide, gallium arsenide, indium arsenide, transition metal dichalcogenides. It only requires that you're able to create a local potential barrier, and so that when you cause spin accumulation by your driving current, one spin species gets over it, the other spin species does not. So we're very excited about this technique, and in fact, this is just about to appear in rapid communication. So, are there any questions on this? There's lots of questions.
Yeah, we have a couple of questions. The question from Mitch Davis.
So, okay. Matt's question is, so the simplest answer is there is an intrinsic spin Hall effect, and way I think about it is that the electron, as it's traveling, is generating the spin-orbit interaction couples the spin and the orbital momentum. But a hand-waving way of saying that is so as the electron's traveling, it's generating its own effective magnetic field, and depending on which way it's spinning, that effective magnetic field will create a Lorentz force either to the right or the left, depending on whether it's spinning in a clockwise or counterclockwise direction. A less exact way of saying it is it's very similar to when you throw a ball and you cause a differential friction if the ball is spinning. There are actually two kinds of spin-Hall effect, intrinsic and extrinsic, but here we're measuring the intrinsic spin-Hall effect, which is due to the band structure and not due to scattering. I think, Dimitri, essentially it's related to a Berry curvature.
I think yes.
Yeah.
The anomalous Hall effect.
Yeah.
Another question by Bernard Field. In the nonlinear technique, how are you able to distinguish between spin and non-spin polarized current? So
I'm not quite sure what this Bernard's question is. I mean, are you asking what would happen if I didn't have, are you asking, can I determine whether the spins are up or down, or are you? So if, for example, if there was no difference, if there was no spin-Hall effect, and I just pass a current along here, I wouldn't end up with a spin accumulation on this side. I would have the same number of spin up as spin down. So the red chemical potential and the blue chemical potential would be the same, and they would have the same transmission probability through this barrier. And I wouldn't end up with any potential difference between the left side and the right side of the barrier. If I was to pass a spin polarized current down down one side of the channel, then yes, you would still pick up this nonlinear effect. But in our case, the spin orbit length is so short that the spins will be completely relaxed within a very short distance. So you actually can't, in systems with very strong spin orbit interaction, it's very difficult to pass a spin polarized current a long direction because the spin orbit interaction very quickly randomizes the spins.
Okay. We have a question from Olivier. Does the symmetry of the sample play a role? So this sample geometry looks quite asymmetric.
It does. So the sample is sort of a K-shaped. The sample's got a slight K-shape, and the reason is that we actually wanted to encourage the spins to diffuse through this barrier. So by putting a slight bend in it, our hope was that it would slightly increase the spin-Hall signal, and it did. Your question is actually particularly relevant because it's not fully appreciated that the spin-Hall angle that comes out of these measurements, everyone goes around quoting, I've got a spin-Hall angle of 7 degrees, and someone else says, well, I've got 10 degrees, so my material system is better than yours because I've got 10 degrees, and 10 is better than 7, obviously. But it rather depends on the geometry you use to measure it, and this is something that's not always understood. You have to be a little bit careful about that. So yes, geometry does matter, but that's not what's, you still see the same thing even if you make it perfectly symmetric. It's just that the results are weaker.
Is it known how much is it enhanced due to this K-shaped compared to the H-shaped?
I think we got an enhancement of maybe a factor of 2, between 50% and a factor of 2. So it's not massive. It's just that already the measurements were taking 30 hours.
I see. It's still quite remarkable. And another question from Abhay Gupta. On the figures on the left bottom corner describing the effect of the quantum point contact is delta divided by mu, same for both approaches?
So in the linear regime, there's almost no splitting. This delta mu, which is the difference between the chemical potential of the spin up and spin down, is almost zero. In the nonlinear regime, you're driving it much harder, so you get a big splitting. So in the linear regime, it will work even for delta mu tending to zero, because what you're using to filter the spins is the fact that the ability of the spins to go through the barrier depends on whether the spin is up or down, because you have a different barrier height for spin up and spin down carriers. And that requires you then to work at high magnetic fields so that you Zeeman split the transmission probability of going through the barrier. In the nonlinear regime, you work at zero magnetic field. So the barrier height is exactly the same for spin up and spin down. And what you have to do is generate a difference in the chemical potential, delta mu s. And that delta mu s is proportional to the amount of current you flow. The more current you flow, the bigger the spin imbalance you create through your spin Hall effect. And what factors this delta mu s depends on is essentially how easy it is for you to, if we go back to our very simple picture of the spin Hall effect, the stronger the spin orbit coupling, the more these will be bent when you pass a current, and so the bigger the spin Hall voltage you will get.
Thank you.
Okay. So, now, I asked Dimitri when the other day how long I should talk for, and he said, well, aim at an hour, and I've only got through half of the talk. So, can people survive if we talk a little bit longer about some new stuff, or?
I think we will be happy to hear it.
Okay, so, all right. If anyone's bored, they can just go away. I can't even tell if you're paying attention, so it makes no difference to me. Poor Dimitri has to sit here and listen, but I'm always happy to talk to him. So, okay, so I'll go, and I'll try not to go too fast and not too slow. So the second thing I want to talk about is a new signature of spin orbit gaps in 1D systems. And this is interesting because these 1D systems have been proposed to be used as topological quantum computers, and topological superconductivity is kind of cool. And the idea is that you can create these anyons, which are neither bosons or fermions. They have non-abelian statistics, which means that the order in which you do operations on them matters. And one of the systems that's been very, very heavily studied is one-dimensional nanowires, where you have a strong spin-orbit coupling. So it's made of a material with, such as indium arsenide or gallium antimonide, where there's a very small band gap. The electron states are heavily connected to the valence band states. That gives you a strong spin-orbit coupling for the electrons. You apply a magnetic field, you add a superconductor in, and you end up with these zero-energy modes. And these are supposed to be topologically non-trivial modes, which have a topological degeneracy, which can be used for quantum computing, because everything is done at zero energy. And what you do, instead of changing the energy of your eigenstates and using those as quantum bits, so say you have spin down and spin up at different energies, and then because you're at different energies, that couples you to decoherence mechanisms, everything is done at exactly zero energy. And all operations are done just by moving things around each other at zero energy. And the idea is that this doesn't couple into decoherence. So what do you have to do to engineer a topologically non-trivial state in 1D systems? There's a very nice proposal from Yuval Orag and Shankar Dasama that you can do it the following way. You can take a low-dimensional disorder, one-dimensional quantum wire. You add in a spin-orbit interaction. So here's my kinetic energy term. Now I have a spin-orbit interaction. We apply a magnetic field perpendicular to the spin-orbit field, and then we couple one end of the wire, we couple superconducting leads into the wire and out of the wire, and we end up with two modes at each end of the wire. And these modes sit exactly at 0 energy. And so there was this very famous experiment by Vincent Murick, who's now at UNSW, using indium arsenide self-assembled nanowires with superconductor evaporated on top, a rather complex device geometry. And what he saw was these two modes come down and then they sit together. And as you increase the magnetic field, this thing just stays exactly at 0 energy. So this is the superconducting gap. As you apply the magnetic field, these two modes come down, coalesce to form this non-trivial Majorana 0 energy mode. So, and similar thing actually, I was in Copenhagen a couple of years ago and we did the same thing using a slightly different approach. So this is all very nice, but one of the prerequisites for doing this is that we have to have a low disorder 1D wire, we have to have strong spin-orbit interaction, and we have to understand what happens when you apply a magnetic field. We require spin mixing, and we require the formation of a spin gap. So what happens is, this is my 1D, these are the E as a function of K in a system with spin-orbit interaction, so the degenerate at K equals 0, and I've lifted the degeneracy away from K equals 0. I apply a magnetic field perpendicular to the spin orbit direction that mixes the blue spin states and the red spin states. And where the blue and red get mixed, we open up this gap here. So now at the chemical potential, I've only got two completely different spin species. And the forward going modes are one spin polarization and the backward going modes are the other spin polarization. And there have been a series of experiments which claim to have observed this spin gap. So how do you actually observe the spin gap? Well, it's kind of easy. This is what I was saying before. This is the E versus K. This is electrons at 0 magnetic field, spin up and spin down, a degenerate. If I apply a magnetic field, I lift the degeneracy between the spin up and the spin down. This we understand. If I don't apply a magnetic field but use a spin orbit field, I split them in K. They're still degenerate at K equals 0. If I have a spin orbit field and I add a magnetic field, then if the magnetic field is parallel to the effective spin orbit field, the blue ones just move up, the red ones move down, nothing happens. But if I put the magnetic field perpendicular to the spin orbit field, then what happens is for a given spin state, if the spin orbit field wants the spin state to point up, and I apply a magnetic field at right angles to it, I will cause that spin state to start precessing. And that precession mixes the spin up and spin down and opens this anti-crossing gap. And so now the forward traveling modes are only spin down, the backward traveling modes are only spin up. And now if I couple a superconductor to this, I will end up with these Majorana 0 modes. What would this look like? In an experiment, if you take a one-dimensional system, you would see that as you change the number of modes in the one-dimensional system, the conductance goes up in steps of 2e squared upon h. If you've opened a spin orbit gap, the conductance goes up to 2e squared upon h, drops down again, and then goes back up again as you go from here to here to here. So the signature one should be looking for is the conductance going up, dropping down, and then going up again. And that should be the signature of the spin orbit gap. Here is the experimental data. This is pretty much the best experimental data that exists. And it's very hard to tell of these bumps and wiggles, which are spin orbit gaps and which are disorder. You want to start with a nice clean system, which is disorder free, and you would want it to be reproducible. But in all the experiments to date, no two self-assembled nanowires show the same features. Everything is getting masked by disorder. So it would be really nice to have a clean system where disorder isn't killing us and we can observe some signatures of the spin gap. So how would we do that? Well, we would probably use holes again. We would use heterostructures. We start off with electrons in a 2D heterostructure. We put gates on the top. We apply a negative voltage to the gates. That forms a constriction here with a little nanowire in the middle. These are the 1D modes inside the nanowire. And you can think of that nanowire as essentially a waveguide for electron waves. And as you change the number of modes in the wire, the current goes up in units of 2e squared upon h, according to Landau-Whittaker. Why don't you just use whole nanowires? Well, the same reason that you don't use self-assembled nanowires. If you make two devices, they rarely show the same behavior. And you end up with all these bumps and wiggles everywhere, even at zero magnetic field. So how on earth are you going to detect one additional bump or wiggle that has developed is quite a challenge. So the first thing is, really, before you go and claim that you are making Majorana modes, it would be nice to have a clear signature of spin gap, and it would be nice to be able to make two devices that behave the same. Then you might be able to scale it up to make a large scale computer. If every device is different, life is a lot harder. So the first thing we did was set out to improve the device reproducibility. We've made quantum point contacts with a narrow nanowire on top of two kinds of wafers. This is the approach that everyone's been using for the last 20 years, where you chemically dope the wafer to create a conducting channel, and then into that channel you form a nanowire. And this is the approach we use, which is no chemical doping. It's more similar to the approach used in graphene now. You electrostatically dope, and you introduce just by gate electrodes the electrons or holes. So here are the results. These are 9 nominally identical, they're actually identical lithography devices made on a doped wafer. And if you zoom in and look for these conductance steps, these traces should all be identical, and they're not. And so if you're now going to start going, well, does some of them have bumps and dips and wiggles due to a spin orbit gap? It's going to be very hard to tell. If we do the same experiment, but we get rid of the doping, we get rid of the unwanted randomness of whether a dopant is on a particular lattice site or not, and we just use electric fields to form the one-dimensional channel, the devices are a lot more uniform. There's still a small offset here, but it's a lot better than the offset in the modulation doped devices. And if we just move all of these sideways so that there's where they have zero current aligns, so we align them all to zero current, this is 9 different devices, all showing exactly the same quantum transport properties. And this is much, much better than anything that has been done before. And we're just publishing this at the moment. So this gives us a good platform from which we can go forward and study spin orbit gaps in systems. What we now need to do is turn the spin orbit interaction on. What I showed you before was electron devices, where we put a positive voltage on the gate to introduce negatively charged electrons. But it's just a parallel plate capacitor, so there's no reason we can't put a negative voltage on the gate and get positively charged holes. And this is work that was done by Jason Chen a few years ago. And this is a gallium arsenide device. This is the carrier density as a function of the gate voltage. And for a positive voltage, we end up with electrons. And for a negative voltage, we end up with holes. And the devices are completely reproducible. You can warm them up, cool them down, everything's the same. If you make a quantum point contact, we get very nice conductance quantization, no nasty bumps or wiggles that would make it hard to detect spin gaps. And if you just reverse the gate voltage on the same device, this is the same thing for the holes now. Again, really nice conductance quantization, no nasty bumps or wiggles. And we can turn the spin orbit strength, which we define as the ratio essentially of the spin orbit interaction to the dwell time in the 1D system, from 0 to approximately 1. How do we now detect this spin orbit gap? We have to apply a magnetic field and open the spin orbit gap. So what happens when we apply the magnetic field? Well, this is the conductance of 0 magnetic field. If we apply the magnetic field, we end up with additional steps because we've lifted the spin degeneracy. And if you just simply take the derivative of this data and plot it as a function of magnetic field and gate voltage, which is essentially energy, you can see really nice linear opening of all your Zeeman gaps. Everything looks good. So you can use this to directly measure the G-factor coupling that Dimitri was asking about earlier. And then I said that it's very dependent on the direction you apply the magnetic field. Well, using a vector magnet system, we can pass the current through a one-dimensional nanowire in holes. And if we apply the magnetic field perpendicular to the current direction, perpendicular to the 2D plane, we actually get a G-factor that's really small. It's about 0. If we apply the magnetic field parallel to the current, then you can see nice linear splitting, Zeeman splitting, and we get a G-factor of about 0.5. If we apply the magnetic field out of the plane, we couple both to the spin and to the orbital motion, so we get a diamagnetic term from the B squared, but we also get quite a large spin splitting. This spin splitting is occurring at 0.8 Tesla, whereas this spin splitting is occurring at 4 Tesla, so this G-factor is much, much bigger. It's about 5. This anisotropy of these two results has just been understood. It wasn't understood for about 10 years, but it is now understood. There's an additional term in the Hamiltonian that we now understand. So we understand pretty well what the spin-orbit interaction is doing in this 1D system. So now let's go and look for a spin gap. So far, what I showed you before was we concentrated on the any more than one subbands. To open a spin-orbit gap for Majorana's, we really have to look at the first subband. So this is electrons. Here's the conductance, and here is the first 1D subband. And if we now look at just what's happening to these 1D subbands, we take the derivative that shows the energy levels, and we can see them splitting nicely as we apply the magnetic field. So this is just linear Zeeman splitting. If we do the same thing for holes, when the field is parallel to the current, what I showed you before is the levels split. Except this first level. It never splits. And for 10 years, we've been publishing papers and never talked about this bit because we didn't understand it. And fortunately, very few of the referees were mean to us and asked us, why is this completely different than this? Or if they did, we just hand waved. But now we know why. It's because we've opened a spin-orbit gap. So Jan van Delft and Olga Gulko have done some beautiful modeling. And they've basically done a tight binding model, introduced a spin-orbit interaction, introduced many body interactions, and they're able to reproduce the data perfectly. So when you have an electron system with no spin-orbit interaction, this is energy, this axis is magnetic field, this is the theoretical calculation. As you apply the magnetic field, you cause a linear Zeeman splitting. This is for 0 electron-electron interaction. If you turn the electron-electron interactions on, you enhance the magnetism, so you get a larger splitting for the same value of magnetic field. And this is the value for electrons. So the electrons here are looking reasonably similar to the calculations. If we do the same thing for holes, what the calculations suggest is that a spin gap does indeed open. And in the calculations, at 0 interaction strength, you get a linear Zeeman splitting, but this upper branch is much weaker than it is for electrons. And if you turn the electron-electron interactions on, this upper branch essentially almost becomes flat. And it becomes flat because this spin gap opens and essentially keeps these two lines flat. Once this spin gap opens, what you end up detecting is this high density of states here and an additional high density of states here. And you don't see this one. And this is the experimental data. And this first subband, even up to very large magnetic fields, doesn't split, just as is seen in the calculations. And so this is work that has been done over many years by Corina Hudson and has finally been published. If you change the orientation of the magnetic field so that it is now not perpendicular to the spin-orbit gap, you should open and close the spin-orbit gap. And so the prediction is that this will give you a new signature for the spin gap. If the spin-orbit interaction is weak, then these two subbands, which are spin split, stay essentially a constant distance apart in energy as we rotate the magnetic field from being perpendicular to the parallel to the current to perpendicular to the current to parallel again. But if the spin-orbit interaction is strong, what happens is that when the magnetic field is parallel to the current and perpendicular to the spin-orbit direction, you open up this spin gap, which is signified by these sort of wing structures here. And when the magnetic field is perpendicular to the current, so it's parallel to the spin-orbit field, you just get a large Zeeman splitting and then no spin gap. And then when you rotate again, so the magnetic field is parallel to the current again, the Zeeman splitting gets a bit weaker and you get this wing structure with the spin gap just up here. And these are the measurements, and with perhaps rose-tinted glasses, you can see that this oval shape feature here, which can only happen when the spin-orbit interaction is very strong. It doesn't happen if the spin-orbit interaction is weak. If the spin-orbit interaction is strong enough to open a spin gap, you get this oval shape, and this is the experimental data. And again, we get this oval shape, and you also get these two wings coming out here, and the spin gap would occur at higher energies. So this is a new robust signature for the spin gap, namely that the first subband appears to not spin split in energy because the spin gap is opening. And so with that, I think it's definitely time to finish and say thank you for attention. We've had a lot of fun doing these measurements. We've demonstrated to you a new way of detecting spin accumulation by a spin valve, a nonlinear spin valve essentially, and a new way of detecting a spin gap opening in a 1D system depending on how you orient the magnetic field. And I think this will be very useful for determining the topological, for investigating topological superconductivity and other things. And with that, thank you very much. Any more questions?
Thank you for very nice talk. Do we have any questions? Let me see. It looks that we don't.
Then I've confused everyone more than enough.
So maybe I have a brief question. So for this, is it anything special happens on the boundaries? So when we consider this original model for the nanowire, what we expect to see something special on the boundaries. Here, in this context, do you have a boundary at all? Could you consider it to be some kind of a boundary?
Right, so this is a really good question. Let me see if I can go back. So in these nanowires that we're making, the nice thing about them is there's a very smooth and adiabatic transition from the 2D region to the 1D region. So there's no, in our technique, there's no essential hard boundaries there is in a nanowire, which gives you essentially organ pipe resonances and reflections. However, there are some calculations from Reynes and Loss looking at the conductance behavior in nanowires with spin-orbit interaction. And what you see is that you end up with these resonances going backwards and forwards as you reflect backwards and forwards off the end of the nanowire. And it makes it super hard to tell whether you've opened a spin gap and caused a dip or whether you're seeing a resonance that's caused the dip. So we work very hard to make sure that we don't have boundaries, that it's nice adiabatic transmission.
Okay, I see. Thank you. We have two more questions. The question from Olivier Blue. Does the observation explanation of the spin gap requires Coulomb interactions between holes?
It does not require, so in experiment, we cannot eliminate the Coulomb interaction. At least, well, yeah, no, I don't think we can very easily. So in reality, we always have a Coulomb interaction, and any model that we create must include that Coulomb interaction if it wants to realistically describe the experiment. The key features of the experiment, the key features of this rotational dependence of this spin gap and the formation of the spin orbit gap, those things don't require Coulomb interaction. Essentially, all Coulomb interactions do is they tend to drive you towards a ferromagnetic ground state. And so they enhance the magnetic susceptibility. So if you look at, say, the difference between this curve, this is just for electrons, so there's no spin orbit. This is without interactions. So this is up to, say, 0 to 4 Tesla, and then 0 to 4 Tesla with interactions. And you can just see that the spin gap, the Zeeman gap, is about twice as big with interactions as without interactions, because interactions tend to favor spin alignment. But it is not necessary. You could just increase the magnetic field twice as large and you would get the same answer.
Okay, thank you. We have a question from Philip Bryden. For the n equal to 1 subband, why do the peaks seem to always be parallel and not to join together at b equal to 0 as predicted by the theory?
Very good question. So this bugged us for very many years. So here is the data that Karina took right at the beginning of her thesis, where she looked at the Zeeman splitting for all different orientations of the magnetic field. And what we always saw is that the higher subbands do a Zeeman splitting, but the ground subband never seems to do a Zeeman splitting, and we could never explain this. So this is exactly the right question to ask. The reason is because of the spin orbit gap. So this one is not splitting. These ones for holes split. For electrons, the ground subband always splits because there's no spin orbit interaction. And the physics of it is, for electrons, when I apply a magnetic field, I just move, the dashed line is energy as a function of K at 0 magnetic field, and then when I apply the magnetic field, the blue goes up in energy, the red goes down in energy. When I turn the spin orbit interaction on, the dashed line is what happens at 0 magnetic field, so I have one like this and one like this. I now apply a magnetic field and I open this spin gap. If you look at the local density of states inside the quantum point contact, it has a peak here at the subband edge, just as you would expect. You would expect that there should be a peak here at this subband, but if you look, this is curving very rapidly, so there's not very many states here. So that peak there is really super weak. That's kind of this one here, this O, and it's quite hard to see. You gain an additional peak just down here, which is this. And that is due to spin mixing at finite K. And so what happens is, you think you're measuring in the experiment the square and the circle, and you think those two should move far apart in magnetic field. But in practice, you're measuring this one and this one. And so those two just stay at a fixed distance. So in the model, when you turn the Coulomb interactions on, the spin gap opens here. This is the spin gap. And then you have this level here, and you have this level here. And that's all we see. So the experimental data is actually quite consistent with the model. The model fails at low magnetic field because it's a functional renormalization group calculation that has to be done at 0 temperature. and our experiments are done at 0.1 Kelvin. And so below a magnetic field equivalent to 0.1 Kelvin, the calculations fail. So they're not, the calculation's not so great here. But above there, this is exactly this. Another way of thinking about it is that at this point, you can't think of spin up and spin down. The spins have been mixed. And because the spins have been mixed, the magnetic field doesn't couple to them. And so there's no Zeeman splitting. So everything just stays perfectly flat.
Thank you. We have another question by Abhay Gupta. I can, why is it perpendicular magnetic field is not at UPC, but at the direction 100?
So I'm not sure I understand that one. Why perpendicular not at QPC? So perpendicular magnetic field is perpendicular to the 2D plane. So the magnetic field is along the 100 crystal axis. That's this one here. This one we don't use so much because it also couples to the orbital motion of the electron, of the holes in the 2D plane. It starts to go round and round in circles. And the circle radius depends on the magnetic field. So you get this curving behavior. So we tend to use the magnetic field parallel to the current direction. And then we get this linear Zeeman splitting. If you apply the magnetic field perpendicular to the current direction, because of the structure of the spin-orbit interaction, actually these k to the fourth terms cancel with the k squared terms, and you get almost no Zeeman splitting. Yeah.
Thank you. I think that we don't have more questions. So let's thank you the speaker again. So only panelists could clap. Yeah. Very nice story. So holes are so different from electrons.
Holes are different, but it's really spin-orbit, right? Spin-orbit is what's interesting. Spin-orbit is what gives us topological insulators. Spin-orbit is what gives us topological superconductivity. Spin-orbit is what's interesting. Holes are just a way of playing with spin-orbit.
Yeah.
So anyway, thank you very much. Thank you, Dimitri, for organizing the talk.
Thank you. And as usual, it is recorded and will be available online in a couple of days. Okay. So bye to everyone. Have a nice day.
Thank you. See you all next week.